Now that we've gone ahead and derived Gibbs phase rule, we're given a chemical process below, and our job is to do an overall mass balance for the entire system. And so that would be kind of exemplified as drawing a big box around all of this and just worrying about our inputs and our outputs to this reaction and not the minute details of the processes happening in between. Now, in order to do this, we need to realize that this is an isopropanol synthesis. And the way that we are going to be able to do this is we have an alkene, this would be propanol, aka C3H6, and we also have water coming in to form the ether, and the ether would look like that, as well as we have, I believe that would be diethyl ether, and then we have isopropanol being formed as well. Now, from here, the first thing to do is to go ahead and write our balanced chemical reactions. So the first thing that's going to happen is we're going to combine our two reactants to go ahead and form our isopropanol here, which we could write as CH3 2 COH, and I guess another way to write that, let's see, we have 3 carbons, 7 hydrogens, or rather 6 hydrogens and 1 alcohol. So we could write it like that as well, I guess. And then we have this side reaction happening here in which that alcohol is being transformed into ether. And that side reaction would also give off some water as well. So we would have water and we would have ether, this diethyl ether here, which would be C4H 1, 2, 3, 4, 5, 10 O. Okay. And now looking at how to balance this here, we have 12, okay, so we need 2 isopropanols there. So these would be the balanced chemical reactions here for this entire system that is happening here. And now our job is going to be to calculate some certain things using some degree of freedom analysis. Now, this prompt here is actually giving us a bunch of measurements that we already have, right? However, the first thing to notice about these measurements, so we're told that we're giving pure propylene and water feed flow rates. So pure means that it's going to be only propylene and only water in those flows. And we're given their flow rates, as well as mole fractions of the alcohol and ether streams. Now the first thing to note is that the mole fraction of this stream does actually not add up to 1. However, this isn't going to be a big deal for us in the long run, as we're going to be solving this numerically anyway. Okay, so we have mole fractions of those streams, and then we want to go ahead and calculate molar flow rates of the ether and alcohol product streams, as well as the extent of the 2 reactions producing isopropanol and diisopropyl ether. Okay, so molar flow rates of the streams, as well as the extents of reaction. Now what we mean by extents here is how many times is that reaction taking place at a molar ratio. So for example, if this top reaction here, and let me actually kind of erase this and move this around a little bit. There we go. So in this top reaction here, if we had an extent of, say, 10, then I would know that 10 moles of propylene were being used, 10 moles of water were being used, and 10 moles of isopropanol were being produced. Similarly, for the bottom reaction, we would multiply all of that by the stoichiometry of that reaction. So we would have 2 times the extent for all of the isopropanols. Now, the extents of the reactions will, of course, vary, and they will indeed be kind of combined into our material balance here. So we need to start kind of formulating the equations that we're going to be using to determine this, and then from that we can determine the amounts of unknowns that we're going to need. Now, we know that we are calculating 4 different things. We're calculating the stream flows as well as the 2 extensive reactions. So from here, I think we need to go ahead and start writing out some of our equations. And I'm going to do this on here first, and then we'll go ahead and transfer that over to Colab in order to actually solve it. So, the first thing that we can talk about is going to be the feeds here, or the inputs, right? Now, the feeds, we can go ahead and say overall. Let me go ahead and put overall here. The feeds minus whatever happens within the reactions themselves. And I'll probably write reactions are xn from here on out. Feeds minus the reactions minus the outputs should give us the overall balance. And these outputs would be the ether alcohol product streams. So let's actually call this products. Input is the feed, output is the product. And this makes sense. This is exactly what we did in our last material balance problems. So from here, all we need to do is we need to make some assertions about the feeds, the reactions, and the products, and then we've solved this system. And we are given a bunch of those different things. So for the feeds, we just need to talk about what are our 2 inputs. So we have our alkene, our propylene, and we have our water. Now, adding those 2 feeds together with their mole fractions correspondingly will give us the total amount of percentages of the different components flowing into the system. However, that's not particularly useful to us. What we need to do is multiply the alkene, let's call it mole fraction, so these are both in the liquid phase. So mole fraction being x. If we multiply that by the stoichiometric ratio within the reactions, so stoichiometric ratio, then we are actually doing what is all in the feed. Now, what is this alkene X? If we go ahead and make that alkene a array, so let's go ahead and define alkene X here. If we make that an array, and we say maybe what's in the first place is the mole fraction of alkene, what's next would be the mole fraction of water, after that would be the mole fraction of ether, after that would be the mole fraction of alcohol. Then we are able to basically use all of our 4 variables, one for each component, right? And we are able to go ahead and multiply that by the stoichiometry of its reaction in order to see how much input we are inputting into this system. Now, for our alkene X, this is really easy. We're told it was pure alkene, so it's only going to have a mole fraction within the alkene section, and then multiplying it by the stoichiometry will solely give it, or I'm sorry, we shouldn't be multiplying it by the stoichiometry. That would be completely useless. That's going to be our reactions. What we need to be doing here is multiplying it by the flow rate. There we are, flow rate. I don't know what I was talking about there. Okay, so multiplying it by the flow rate will give us how much we're putting in, right? Flow rate is going to be, I believe in this problem, it is moles per second, which is rare, however super nice for us because it means we're having to multiply by less constants here. So we have moles per second, and then this is going to be some sort of mole fraction here. And so from that, I believe we should be getting moles going into the system. Yes. So we're doing everything in units of moles here. Okay, so that takes care of our feeds. Now let's look at our reactions here. For our reactions, we have two reactions happening. I'm just going to denote this as reaction 1 and this is reaction 2. There we are. So for reaction 1, if we go ahead and multiply, let's see, we can just go ahead and multiply our stoichiometry of the reaction multiplied by the extent of the reaction here. And by multiplying by the extent, we are, again, stoichiometry should basically be unitless. Extent will be in moles, so now we're talking about how many moles are going to be entering or leaving the system. For the stoichiometry of the first reaction, we would put in all of our reactants as negative numbers, so it would be -1, -1. Let's see, we said ether is next, there's no ether being produced here, and then alcohol. And alcohol will be a positive 1. And so that would be our stoichiometry of reaction 1. Here. There we are. Similarly, for reaction 2, we would do exactly the same thing, multiply the stoich by the extent. I'm not going to write that down here. And then finally, we need to talk about the products. The products, we have, again, basically the stream, so ether stream, mole fractions, multiplied by its flow rate. And then we have the ether stream, or rather the alcohol stream, its mole fractions multiplied by its flow rate. And again, we are given the mole fractions, I believe. Yes, we're given the mole fractions, and our job is to calculate the flow rates. Now, we should have, from here, we have how many equations? 1, 2, 3, 4, 5, 6 equations, with each one kind of containing 4 unknowns. So we have more than enough degrees of freedom with which to solve for 4 of our unknowns here. Okay, now, at this point, I believe we can actually transfer over to Colaboratory and actually start coding this out. So here we are in Colab, and you're going to see I've already imported a bunch of stuff up top, and I'll explain the imports from that I will use as I go through them. And I'm also going to go ahead and import NumPy, as well as import our root solver function, for which I plan to use to solve these equations. And I spelled something wrong. Oh, from. There we go. Alright, so from there, haha, look at that little segue. I now plan to go ahead and write down all of our variables. And at this point, it is quite important that I mention we are going to be using a dot dictionary. So I'll call this E is equal to our dot dictionary up there. And the reason that I'm going ahead and doing that is that I can use all of these variables, I can import them into this dictionary, and then I can call them all to import them into one function, and I can just reference the dictionary as the input to that function. And that function, which we will be writing in a second, will refer to all of our equations that we've created earlier. But first, let's go ahead and write down all of our variables. Now, as I referred to previously, we were going to go ahead and write these as arrays. And let's go ahead and start with our input streams, input feed streams, right? So first we need to go ahead and put our molar flow of alkene, and we're going to reference in here the mole fractions of each component within this array. So I'm going to reference this as our dot dictionary, and we are going to pull an array here. And we have 1 mole of, or all of this stream, we were told it was pure propylene, which means it's going to be all alkene there. Similarly for water, it's going to be liquid mole fractions, and we can go ahead and make an array for it. Its array will be consisting of zeros, and it's 1. It is completely pure water. Now we also have flow rates for these, so we can say alkene flow rate here, and we are going to go ahead and call these flow rates. Let's see, we are actually given these, so it's 100 moles per second, and then for the water flow rate, we are told it is 95 moles per second there. So that takes care of all of our input material, and now let's go ahead and focus on our reactions. Reactions, there we go. Now, in our reactions, we need to know our stoichiometries here. So let's go ahead and write that E dot stoich of reaction 1. And what that is going to be, it's going to be another array here. And in this array, we can go ahead and put what? Let's go ahead and put our alkene, that's going to be a -1. Let's see, what did they put here? Ether is next, is 0. Remember, this is the first reaction, this was the top one. Our alcohol is 1, and then our water is -1. Similarly, let's do this for reaction 2 here, stoich of reaction 2, and let's call that another array. And in this array, let's see, we're not going to have anything to do with the propylene. Let's see, next is ether. We're going to be producing 1 ether. We're going to be producing -2 alcohol and 1 water there. Okay. And now, let's go ahead and put in the extents. We can call it E dot extent of reaction 1. That works. And we'll make that a range variable because it is an unknown. And so for this range variable, we're required to provide an initial guess and then a low and a high of our range. Now the initial guess is not particularly important, and so in this case I am just going to go ahead and put in 100. And then for the low I'll put 0, and for the high actually I'll put 100 and then make the initial guess. Let's make that 50. And so that's basically the exact middle of the range from 0. Obviously it can't be less than 0 because it has to be reacting to some extent. And then the top here is the molar flow rate of the alkene. And so it can't possibly be larger than that. Similarly, let's do kind of the same thing for reaction 2. This one should be happening less because it is not our our desired product is not occurring from that reaction. In fact, it's actually using up our desired product there. So that takes care of our reactions. Let's go ahead and now and do our product output streams. And from here, we just need to go ahead and basically do the same things that we did up here, except this time we are going to do ether and alcohol. And so to start with our ether, we are actually given the mole fractions of these two streams. So the ether is 0.001 for the propylene, 0.9 for the ether, 0.09 for the alcohol, and 0.01 for the water. And then for the alcohol product stream, 0.001 for propylene, 0.01 for the ether, and then let's go ahead and do 0.01, 0.94 then, oops, for the alcohol, and finally 0.049 for the water. And I'm going to go ahead and actually, now I'm thinking about it, just because this just popped into my head, I'll put decimal places. Oh, maybe I shouldn't do that. I don't know. Sometimes I've seen my professor put decimal places after the numbers there, and it works out in his favor. We may have to do that later. Who knows? Okay, and then these are going to be range variables again for these two flow rates. For the ether stream, I'm just going to give it a nice low flow rate of 5. Again, the ether is not our desired product. And then 0 to, let's say, 50 can be our range there. And then for the alcohol, same kind of deal, 50, and then 0 to maybe 100 can be our range there. And from that, we've gone ahead and done all of our variables. And at this point, we're just going to go ahead and define our equations here, inputting some sort of dictionary. Now, again, what we're trying to return is the feed plus the reactions. We did the stoichiometry negative, so we'll add the reactions there, and then we'll subtract the product flow. Oh, didn't want to do that. Autocorrect screwing me over. Now, from here, all we need to go ahead and do is define our feed, define our reactions, and define our products. Now, the feed here is going to be the alkene molar flow rate times its mole fraction, and I am writing that in the opposite way that I said that. I realized that. And then to that we want to add our water mole fraction multiplied by our water flow rate. And I'm going to spread all this out here. There we go. So that's going to be our feeds. As far as our reactions, we said it was going to be our stoichiometry multiplied by our extent. So E dot stoich, reaction 1, multiplied by E dot extent of reaction 1. Yes, and then added to that E dot extent of reaction 2 there, multiplied by, oops, and I'm using E's instead of D's, which is going to confuse everyone involved. So the extent then multiplied by the stoichiometry of reaction 2. Now for products. For products, again, same kind of deal as our feeds. E dot D dot ether flow rate multiplied by D dot ether mole fraction. Added to that will be our alcohol flow rate multiplied by our alcohol mole fraction. Now, that should go ahead and work out for us there. Now what we're going to go ahead and do is, I think I need to add this block in here, is I want to go ahead and basically pull out a bunch of different things here. Each x to nt, wrap, I believe, x to unknown, and const are all going to be part of this d to nt. So basically what I'm doing here is I'm changing our dictionary E into a named tuple, and then I'm splitting that into a bunch of different parts. Now these parts are useful because we're now going to use this wrap function here to wrap our equations up with our variables. And so we can call this then wrapped equations. Okay, and then from there all we are going to have to do And then from here, all we're going to do is basically use our root solver to solve our wrapped equations function. And x naught will go ahead and be our initial guess there. That's what we pulled out of that dictionary to named tuple function earlier. And we only need to actually take the x values out of this. It's going to spit out a bunch of different roots. We only need the x's, as that is going to be what are the actual numbers in our equation. And we can just call this maybe x here and hope that works. Oh, thank goodness it did. Okay, so now what we need to go ahead and do, we can do x2 unknown of x, and this is going to show us all of the things we were attempting to solve for here. There we are. So again, this shows us the extent of our reaction for both reactants, and then our ether flow rate and our alcohol flow rate. Similarly, we could also do x2, I believe we could also do constant of x, maybe? Okay, maybe not. I was going to try and pull out all the constants, but I don't know that that is possible from here. Okay, but there it is. There is all of the answers to our overall system here. We found the flow rates of the ether and the alcohol streams, and now I think we're finally ready to move on to the most difficult challenge yet, which is going to be to move into the material balance of each reactor. I'll see you in that video. See you soon.